In module 3, we will discuss the theoretical basis of solar magnetohydrodynamics, and in this module we will be working with quite a few equations. So, what we would like to do is to start off from Maxwell's equations, and from there we would go to the induction equation, which is a very fundamental equation for MHD systems, and we will try to understand, based on the induction equation, how different systems can sustain magnetic field creation, why some systems can and some systems cannot produce magnetic dynamo action. Okay. So, what you see here is the full set of Maxwell's equations, tells you how the electromagnetic fields are related to each other. Now, this is something that you are used to seeing. So, for example, in the Ampere's law, if you are dealing with systems which is a non-relativistic plasma, the displacement term would drop off. So, you have just the one involving the current density mu 0 j remaining. And similarly, if you are dealing with a system, a plasma system, which is overall charge neutral. So, if you take sort of a small region of this and you find overall charge neutrality, the charges in ions as well as electrons, then the Poisson's equation becomes redundant and you can essentially get rid of that. And then you sort of have this 3 Maxwell's equations remaining, which are still sort of relevant in this kind of a plasma system. And the other one that is relevant when you have motion is the Ohm's law, which relates the current density to electric field and magnetic field when you have conductor or a plasma system. Now, play with these equations that are remaining with you and the Ohm's law, try to get rid of the electric field and the current density and get relationship between the magnetic field and how this relates to the velocity of the medium, then you will essentially end up with what is known as the magnetic induction equation. So, this induction equation is the most fundamental equation in MHD, and what this relates the time evolution of the magnetic field B, which is in principle a function of space, given plasma velocity V, which appears on the right hand side of the equation, and the diffusivity in the system eta. The diffusivity there can be also visualized in terms of the inverse of the product of the permeability and conductivity. So, this is like the inverse of conductivity of the plasma. So, if you have a highly conducting plasma, then the diffusivity eta is sort of low, right. And of course, you have the divergence free condition still valid, which essentially implies that flux is conserved in the system. So, when you are dealing with a fluid system such as a plasma system in the interior of stars or the atmosphere of a star, there is of course a motion of the system. The question is what drives the motion. There can be various kind of forces which is driving the motion, and in fluid dynamics, for example, if you want to look at the evolution of the velocity fields in a flow, then you deal with the Navier-Stokes equation. And of course, this is an equation that is fundamental to also magnetohydrodynamics, in the sense that even the plasma flows are governed by this equation, and this equation relates the conservation of momentum to which is like del V del T, how the momentum changes, that is related to the influx of or the outflow of momentum. The balance of this is determined by various kind of forces such as pressure forces, forces acting on the surface, body forces which are acting throughout the volume. Body forces are typically large scale forces like gravity or the Coriolis force, and then finally the viscous force, which is really a dissipative force in the sense that it sort of tries to destroy motion. So, you have some forces which are driving the fluid flow and some forces which are trying to stop the fluid flow. So, often in astrophysical systems, in some systems gravity could be important, and often in some systems you are dealing with other forces which dominate the gravitational force, especially where the density stratification is low. In this case, you can basically get rid of the gravity term when this happens. And in systems, plasma systems, where magnetic fields are present, there are 2 important changes that is brought about to the Navier-Stokes equation. Right now, what you are seeing is the fluid Navier-Stokes equation, not for plasmas. If I consider this for plasmas, then I introduce 2 additional terms, and these are the 2 additional terms. So, the first term there is B square by 8 pi is the magnetic pressure, adds on to the fluid pressure, and then you have the other term, which is the magnetic tension force, sort of becomes an additional force to reckon with in MHD or magnetohydrodynamic systems. And this essentially arises from expansion of the Lorentz forces, which involve the magnetic field that is there in the plasma system. Once you have the Navier-Stokes equation, you know how the flow is evolving, and you also need the energy equation to kind of constrain the dynamics of energy transfer amongst various different forms. And this is important because the flux of energy also drives flows, and this is of course encapsulated in the energy equation, which often one has to consider with the equation of state when you have for example a system that can be treated as a ideal system. You would assume the ideal gas law as your equation of state, for example. So in this equation that you see here on the right hand side, the Q sort of denotes the source or sinks of thermal energy. The interesting thing in MHD systems is typically in these systems Q, this source, also encapsulates the magnetically mediated heating, which is a result of ohmic dissipation. So typically you sort of add a J square by sigma term in the right hand side when there is dissipation, which is proportional to the square of the current density. So that sort of takes care of magnetically mediated heating, which is something that is very important, for example, in the sun's outer atmosphere. Often when you have a very good idea of how the different energy flux is related to the flows and you can measure the flows directly, you don't really worry so much about the energy equation. You can use adequate boundary conditions and not consider the energy equation at all, you know, you can take advantage of the fact that in MHD systems energy is actually stored within magnetic field lines itself. So the dynamics of magnetic fields, their dissipation can in fact be a source of energy within the system itself, in which case you can just get away by not worrying about this equation per se, but just dealing with in terms of the magnetic field dynamics. Finally, you have the continuity equation, which is of course something that is valid across neutral fluids as well as plasmas. The continuity equation in case of plasmas can in fact also be broken down to portray independently the conservation of ions and electrons in the system. You can also express it in terms of just a simple mass conservation equation, because that is also valid, along with the fact that the number of ions and electrons would be conserved in a plasma system. And this is important especially in those domains where there is a strong stratification and your density is changing, and if the density changes and you have large scale flows, this has an impact on the mass flux based on whether when a fluid is compressible or incompressible. This can have different implications for how the flows change with changing velocities, right. So the continuity equation is also something that is very important, and one has to consider this as part of your MHD system as well. So there's some assumptions which go in when you are writing down the system of equations that describe an MHD system, and the very application of the concepts of MHD are sort of reliant upon these assumptions to be valid. So for the case where you are dealing with non-relativistic MHD, the kind of equations we have written down here, which we are going to describe, the assumption is that relativistic effects are not important. So most of the velocities that we are dealing with, or the masses that we are dealing with, do not take the system anywhere close to extreme systems where relativity becomes. Additional assumptions are that the collisional frequency in the plasma that you are dealing with is small compared to the plasma frequency, and that the plasma is a continuum with the system length scale being much bigger than the ion gyro radius. And what these assumptions imply is that you are not really seeing any single charge in motion, or you are not seeing their oscillation. What you are really seeing is this whole system, not single charge, and this assumption is important in terms of dealing with this whole system as a single fluid. The other assumption that you have is the plasma is in thermodynamic equilibrium, which sort of allows you to write down an equation of state for it also and relate the pressure, density, temperatures. This is valid when the time scale of interest for the phenomena that you are studying with this MHD system is much larger than the collisional time scale. Or equivalently, when the length scale of the system is much larger than the mean free path of particles which constitute that system, implying that there is enough time available for thermodynamic equilibrium to be reached in this system. And finally, you explicitly call this condition that the plasma is a single fluid, which implies the length scale of the system to which you are applying this magnetohydrodynamic equations to understand its dynamics, that length scale of the system must be much larger than the Debye's length in the system. Why is that? So, Debye's length is really a sort of a charge shielding length scale. It expresses through a very precise relationship between various parameters, including number density and the temperature of the system, over what distance the separation of charges is felt. For example, the Debye's length is denoted here by lambda d. Over this distance lambda d, I can feel the Coulomb force of ion or electron in the system. Typically, it is an ion around which electron cloud will conglomerate, right. If I can feel its Coulomb force. Beyond the Debye's length, this charge that is there at the center of this electron cloud, the ion, the charge of that ion is effectively shielded by this electron cloud. So, you do not really feel the presence of this charge beyond that distance. And over this length scale, beyond lambda d, right, you are really seeing a single fluid in the sense that you have an ion which is balanced out, whose electric field is being balanced out by this electron cloud, and therefore, this appears as sort of a single fluid system to you, where ions and electrons do not have to be treated as separate entities. Okay. Typically, the potential falls off much faster in such cases because of the presence of the electron cloud, and over a distance of lambda d, force of the charge that is in the center of the ion is effectively wiped out. So, that when you are considering a length scale which is much larger than lambda d, the Debye's length, you are fine treating this system effectively as a single sort of fluid. Okay. So, with these ideas in the background, you can write down the complete set of MHD equations now, which is what is there in the slide. The first one is the continuity equation, followed by the Navier-Stokes equation in its full form with the magnetic pressure and magnetic forces present. Subsequently, the energy equation which quantifies energy conservation, the magnetic induction equation, which is the most important equation in MHD, and of course, this is all valid along with the free condition divergence of B is equal to 0. So, if you want to solve the full set of full MHD system, this is what what you would like to do is to solve all of these equations together simultaneously, and because these are all coupled equations, nonlinear, what you have to do is you have to take recourse to computation if you want to do this all at the same time. Okay. So, what we can do is we can break up this system into different and take individual equations and study their properties to kind of get a physical insight of how these systems would behave in certain certain extremes or certain conditions which we may assume, right. So, for example, if I look at the induction equation, the magnetic induction equation, I have two terms on the right hand side. The first term involves the curl of V cross B, where V is the velocity of the plasma. The second term involves the eta lambda square B, where eta is the diffusivity of the plasma. Now, if I take the ratio of the dimensions of the first term and the second term, keeping the velocity as V and the diffusivity as eta, then the ratio of the first term to the second term on the right hand side of the induction equation comes out to be a dimensionless number known as the magnetic Reynolds number, which is the product of the velocity and length scale of the system and divided by the diffusivity of the system. Okay. So, you can imagine that in astrophysical systems, the magnetic Reynolds number is very high, because typically the length scales are much relatively much larger, and also the velocities are high in astrophysical systems. You expect Reynolds number to be high and such. You can take an approximation that I am dealing with a very low Reynolds number system, where Reynolds number is very low, which is possible in laboratory systems, for example, right, or systems with very high viscosity over small length scales. So, if your Reynolds number is very low, essentially this implies the second term dominates in this equation, the first term is almost negligible. A second term here is eta lambda square b term. When that is the case, in the most extreme case, you can reduce your equation to just that term there, which then essentially implies that del b del t is equal to eta lambda square b, which is very similar to the diffusion equation in its form, if you note it. And it is indeed true that what this implies is, if this is the only remaining term, then any initially existing magnetic field at a given point in time will essentially diffusively decay with a characteristic time scale, which is governed by the diffusion coefficient eta and goes as L square by eta, right. So, higher the diffusion coefficient, the faster will be the decay of this magnetic field, and essentially after some time, which is many times diffusion time scale, you would expect that the magnetic field would be completely wiped out, right, in this system. So, essentially this is like a sink term, right, the diffusion term, where if you do not have any source and if this is the only term, eventually at some point in time in the future, you will have no magnetic field remaining in the system, right. Which sort of tells you also that if you have to evolve this equation and you have to have a growth of magnetic field, then the first term on the right hand side of this equation, the curl of V cross term, is very important. The source must be contained in that, right. Okay. So, we can take the other extreme and see what happens in the domain of very high magnetic Reynolds number. So, Rm is very high, you can essentially then say that, okay, fine, that means my first term here, curl of V cross B, is dominating over the second term. So, I can neglect the second term altogether. My equation reduces to this, del B del T is equal to curl of V cross B, which is right here, right. Now, you can show this explicitly, that if any arbitrary field, vector field, del F del T, where F is the any arbitrary field, satisfies the equation that del F del T is equal to curl of V cross F, then the flux of that field across any surface while that surface is moving along with the fluid flow is essentially invariant, right. What this implies is that in this case the flux of the field, which is B, is the magnetic flux, right. So, what this implies is, if I have a condition where I can neglect the diffusivity term and the Reynolds number is very high, which allows you to do this, then the flux of B over any closed surface is invariant as you follow this surface while this is moving with the plasma flows, right. This implies that magnetic field lines are frozen to the plasma flows, or magnetic flux is conserved over any surface as it moves with the plasma flow, right. So, this is known as the Alfvén's theorem of flux freezing, and this plays a very important role, because in plasma systems with high magnetic Reynolds number, this allows the plasma to move the magnetic fields along with them, twist them, turn them, stretch them, shear them, which plays very important roles in the generation and dynamics of magnetic fields in astrophysics across stars, galaxies, and in planetary interiors. Just to kind of bring that point home, in this slide, what we do is we expand the continuity equation to give you an idea through analogy of what these different terms are, right. So, I have on the top here, del rho del T is equal to minus rho divergence of V minus V dot gradient of rho, right. So, what the first term here on the right hand side of this equation is telling you, this equation here, is how the density here rho changes in time as there is diverging or converging flows into that region, right. So, for example, if I have converging flows into the region, the density there will increase. If I have diverging flows, then the density in that region will decrease. The second term on the right hand side, V dot grad rho, tells you how the density in this region will change when a particular flow physically brings in, which is often in fluid dynamical parlance is referred to as advect. When it advects a region of different density into this space, right. So, if I am looking at the change in density in this region and the flow is moving from this direction to this direction, and the density here is lower, and eventually over time this low density region is moved here by the flow, fluid flow, then the density here will reduce as well, right. So, That's what the second term on the right hand side of this equation is telling you, right. Similarly, the induction equation, when I do not consider the diffusivity, I can expand the curl of V cross B term into different additional terms, and I get a divergence of B term, which tells you, so this is right here, the first term here, which tells you how the magnetic field B changes when the fluid flow is diverging and squeezes together the magnetic field, which will increase the field strength, right. And when it's not converging but diverging, it will take apart the magnetic field, thus decreasing its strength, right. The second term here is just the advection term, which tells you how the magnetic field in a particular region will change because of the plasma flow physically bringing in magnetic field from another region into the region of interest. And the last term there, B dot nabla V, encapsulates the role of shear. So, when I have a velocity shear, that will also change the field, but it will change the field in the way that it typically generates a new component of the field from another component of the field. Okay. And this plays a very important role in stars where there is differential rotation, and the shear in the rotation creates a component of the field from another component. We will talk about that in greater detail when we go to the next module. When we go from the interior of stars to the exterior, although we are still dealing with the same MHD system, there are some fundamental differences which come out when you look at MHD equilibria. Okay? And this is something that is sort of quantified through the plasma beta parameter, which expresses the ratio of the gas pressure to the magnetic pressure in the system. So, for example, if you have the full MHD system with the Navier-Stokes equation, we have to consider the magnetic terms as well, right. So, we have the magnetic terms in the Navier-Stokes equation, which you see here, right. Okay. Now, let us consider that we are dealing with a system where gravity is not so important, the magnetic forces are important, and we neglect gravity, and we say that we have reached an equilibrium, right. Equilibrium implies there are no flows and there is no del del t term, there is no time variance, right. So, when you get rid of the velocity terms, the time variant del del t terms, then this Navier-Stokes equation here, which is fairly complicated, eventually reduces to this very simple form here, right, which is just nabla P is equal to some function of curl of B cross B, right. Now, P here on the left hand side of the equation is the gas pressure, right. So, this denotes a situation where you are in equilibrium by virtue of the fact that this is a gas pressure balanced scenario, where the gas pressure and the gradient or the special distribution of the gas pressure is such that the forces that arise because of that are balanced out by the magnetic forces. And in such a scenario, the plasma beta parameter plays a very important role, because if your plasma beta parameter is very high, it tells you that the gas pressure is very high and plays an important role in the dynamics. On the other hand, if the plasma beta parameter is very low, then it tells you that the gas pressure is very low and is the magnetic field pressure and the magnetic field which dominates the dynamics. Okay. All right. So, let us first consider the high beta scenario where your gas pressure is very high. So, when your gas pressure is very high, the gas pressure plays a dominant role in the dynamics, and it can actually hold magnetic fields together and produce coherent magnetic flux tubes and not let them expand. Okay? And this is what happens in the interior of stars like the sun, where I expect to find coherent magnetic flux tubes which is held in pressure balance with the fluid pressure or the plasma pressure which arises because of which is the thermal pressure really, it is in balance with that. So, the thermal pressure holds together a magnetic flux tube through mechanical equilibrium across its bounding surface, right. And when this happens, this implies that the gas plays a dominant role in the dynamics. Not only can it hold magnetic fields together, it can actually push them, jostle them, move them around and play with the magnetic fields. And this is something that is important because this allows the plasma to inject the kinetic energy that it has into changing the magnetic field. And this is fundamental to the production of magnetic fields, and this is something that is quite important in the interior of stars where magnetic fields are produced. Okay. We can go to the other extreme, considering the domain where plasma beta parameter is very low, implying the gas pressure is very low and the magnetic pressure is very high. This naturally happens in the exterior of stars where the density is very low, right, because the number density of particles is very low. So, the solar atmosphere, outer atmosphere, from the upper chromosphere to the corona, you expect that the plasma beta parameter is very low because the magnetic pressure is high, the gas pressure is very low. When this happens, in the pressure balance equation where namla P is equal to curl of B cross B by 4 pi, you can essentially neglect the left hand side of the equation, the namla P term, right, in which case that equation reduces to curl of B cross B is equal to 0. Right. So, in a situation where magnetic pressure is dominating the dynamics, you can neglect the gas pressure and this is what you have. The two possible solutions to that equation, curl of B cross B is equal to 0. The first is the trivial solution that curl of B is equal to 0. Now, if you remember the Ampere's law, curl of B is equal to mu 0 j, which implies that if curl of B is equal to 0, this system does not host any currents. So, this is a current free system. This is also known as the potential field solution to the system, right. So, you would expect then that the minimum energy configuration, which is in equilibrium in outer atmospheres of stars like the sun, could be like a potential field solution, which is governed by curl of B is equal to 0, right. The other possibility is that the curl of B is in the same direction as B. So, curl of B is equal to alpha B, where alpha is a scalar, right. This is a second possibility and this still satisfies curl of B cross B is equal to 0. And in this situation what this implies is there are currents, but these currents are aligned along with the direction of the magnetic field. And in this case alpha, which is the scalar parameter in this equation, can be shown to be related to the twist of the magnetic field lines. As the magnetic field lines is moving along the flux tube, if it is twisted, then it will have a non-zero or finite value of alpha. This also signifies helicity content in the magnetic field lines, and we know that this plays an important role in the dynamics of magnetic flux tubes in the outer atmosphere of the sun. That magnetic field lines can be twisted, they can be helical, which stores some excess energy over the potential field, which is available for release in for example, heating the solar corona or powering solar storms, right. So, the minimum energy state that is possible in the outer atmosphere is the potential field, curl of B is equal to 0. Any state that has more energy than the potential field can potentially relax to the potential field configuration and thereby release energy to either heat the solar outer atmosphere through some dissipative process or perhaps even power instabilities and energetic events which result in solar storms. So, one drastic dissipation mechanism is to get rid of the magnetic fields by directly bringing oppositely directed or somewhat differently directed magnetic fields together, right. And this process is known as magnetic reconnection, and the most efficient form of magnetic reconnection is depicted in this cartoon figure here, where the blue and the red lines denote oppositely directed magnetic field lines, which are being pushed together from the top and the bottom with this converging plasma flow, and when they come in touch with each other, you see them reconnect, because you cannot really have a X point where magnetic fields are going in 4 different directions, or even a single point where magnetic fields are going in 2 different directions. So, if you push them together, they have to reconnect, and when they reconnect, you have this diverging flows and field lines from the 2 sides of this reconnecting region. But in this process, you most certainly end up losing some magnetic fields right here in the center of this domain, right there, right, where you are pushing and making them converge and creating a big gradient in the magnetic fields. So, you produce what is known as a current sheet there with very strong currents where the magnetic field gets dissipated and energy cannot be destroyed. So, the magnetic energy is converted to thermal energy, which then heats up the plasma in that region, accelerates charged particles from that region, and so essentially what this does, it allows the plasma to radiate out photons when it gets very hot, and depending on how hot it is, it could be radiating anything from visible to ultraviolet to extreme ultraviolet to X-ray photons, and this process essentially is what gives rise to coronal heating in the corona, this magnetically mediated release of energy, eventually heating the corona to million degrees such that X-rays are sort of released from the coronal layers. And it's believed that this also plays a very important role in driving very massive solar storms, because a lot of energy that's available in the flux loops over active regions or sunspots can be dissipated through this magnetic reconnection to power this solar storms. Okay. With that, we end this module, and here is a list of resources that you can read, starting off with the book, 2 different books dealing with fluids and plasma physics and magnetohydrodynamics, and you also have references to online materials where you can read more about MHD and magnetic reconnection. In this module, we will discuss more details about the magnetic field generation process in the sun and how we model this and how we understand it in terms of some basic principles that follows from the magnetohydrodynamic considerations that we have discussed earlier in the last module. So, before we focus on magnetic field generation in the sun, let us talk of magnetic fields in the universe a little bit, because it kind of provides context for us to understand where do magnetic fields in the in the cosmic scale come from. I think it's sort of obvious to some extent that in any astrophysical system where there is a variability in magnetic fields, the magnetic fields are either being created or destroyed. So, in this context, the 2 important things that we should keep in mind. One is that astrophysical magnetic fields exist at different scales, starting from the largest scales of the universe to the smallest scales of the planet, and that their variability also exhibits very different kind of behaviors. In some systems, they are relatively constant in the sense they do not change much over the evolutionary lifetime of the system. For some systems, for example, the sun, the magnetic fields are highly variable, and they change much more rapidly than a relevant evolutionary time scale in the system. So, in the cosmological context, it is believed that magnetic fields early on resulted from a coupling between photons and electrons, which was mediated by a cosmological density fluctuations when the visible universe sort of emerged about 370,000 years following the Big Bang. Different estimates and measurements from based on these fluctuations sort of pin down this magnetic field at which is on the order of something like 10 to the minus 18 Gauss. Now, this is extremely small, but this is also at a point in time, this is something that was essentially present all across the universe. So, it existed over large scales and still probably exists over very large scales, and this is something that is very important in the early history of the universe, because this would have provided seed magnetic fields to be amplified either via the collapse when compact objects such as stars were forming out of a very tenuous molecular cloud. This is something that can also provide the seed for dynamo action for magnetic field to be amplified out of the seed field via various processes that draw energy from for example, let us say the kinetic energy of plasma flows. When we go to smaller scales, from the scales of the universe, for example, scales of galaxies, we know that there are magnetic fields in the galaxies which are in fact aligned, for example, along the spiral arms in such spiral galaxies, and that these magnetic fields do play a dynamically important role in for example, the structuring of the gas, the plasma and star formation. This magnetic field is on the order of 10 to the minus 6 Gauss, and it is thought that there is dynamo action in galaxies, implying that there is a mechanism which amplifies the seed magnetic field in galaxies to these levels that are observed. And uh, rigorous numerical simulations and theoretical ideas have shown that supernova explosions play a very important role in this process in the galactic dynamo to amplify weaker fields to these levels of 10 to the minus 6 Gauss, what is thought to permeate the scales of the galaxy. When you come to much more smaller scales compared to galaxies of stars, for example, and talk of solar type stars, but which are rotating at different speeds, we see a range of diverse activity levels. For example, you have two stars on the top of this plot here. So, these two stars show a very high activity level, but which does not vary in time much. It is sort of, well, it does vary, but that variability is sort of irregular. There is no periodicity or predictability to that activity level, right. When you look at the stars which are in the middle panel, these two stars, you see that they are actually variable and they are periodically variable, right, in the sense that the variability is periodic, much like the sun's magnetic activity level. And then you have some stars which have very weak activity levels and they appear completely flat in the sense that there is no variability. Sort of sometimes people talk of them as Monroe minima stars. So, the Monroe minima was a phase when the sun had no sunspots. This is between 1645 and 1715 AD, when it is thought that the magnetic activity level in the sun died down. So, these stars are referred to as Monroe minima stars. The stars in the middle panel are like the sun, whereas the ones on the top panel, which are very highly active, but very irregular with no sort of regularity or periodicity in its activity, are very fast rotators. So, what is now known as the typically fast rotators, or the sun when it was young and it was rotating much faster than its current stage, produce much stronger activity in terms of its magnetic output. Stars which rotate like the sun are more like moderate, and then when they slow down, the magnetic activity levels fall even further. In fact, there is a nice relationship between the magnetic output and the Rossby number that is gleaned from observations, and is also nicely explained by dynamo theory across a range of observations in stars, implying that dynamo is a universal process, not just in the sun, but across solar like stars, which sort of conform to certain universality in terms of how the activity levels scale with the Rossby number across a diversity of stars. There are certain stars like neutron stars and pulsars, which are compact objects and the end products of a massive explosion, like a supernova explosion of a massive star, a star much more massive than the sun. Now, typically a neutron star exhibits very strong magnetic field. They are very small in size, typical radius is below 10 kilometers. They spin very fast on the order of milliseconds, and they have extremely strong magnetic fields on the order of 10 to the power 12 Gauss. There are of course also a new discovery called magnetars, which have even stronger magnetic fields, 10 to the power 15 Gauss. And pulsars are those neutron stars which are seen to emit periodic pulses, and this is something that has fascinated astrophysicists for a long time as well. In this case, however, in the cases of pulsars or neutron stars, we do not see much variability in the magnetic field amplitude or distribution, and it is thought that these fields pretty much are constant over very long time scales, which are comparable to the evolutionary time scale of the system, and that therefore, they are not a product of dynamo action, but rather that they are a product of the collapse of a much more massive star with a smaller magnetic field into a much more compact star. But since this is a plasma object with very high conductivity, during the collapse process, the magnetic field remains frozen in the plasma, and by virtue of the fact that the area decreases, the magnetic field strength increases quite a bit to generate the kind of field strength that is now observed in neutron stars or pulsars. At the smaller scales in astrophysics, we have the planets, and taking the Earth as an example, we know that the Earth has a magnetic field which is comparatively small compared to the magnetic fields of stars, for example. It is on the order of few tenths of milligauss, and that this field is roughly dipolar, with the polarity of the Earth's magnetic field reversing something like every 200,000 years. We know that this is the result of dynamo action, because if the magnetic fields were not being continuously created, given the typical conductivity of the Earth's liquid outer core, the magnetic fields would have decayed in about 20,000 years. The fact that these magnetic fields have existed over billions of years tells you that there is a process of magnetic field creation. So, there is a geodynamo which presumably operates in the liquid outer core, where plasma the motion of this conducting iron nickel core is possible to kind of feed a dynamo mechanism to generate the magnetic field. It is important that we have a magnetosphere, a magnetic field that permeates our atmosphere, because this magnetosphere protects us from high energy charged particles. For example, it protects us to some extent from cosmic rays, to a large extent I would say protects us from the solar wind, right, which would otherwise interact directly with the neutral atmosphere and strip away the atmosphere slowly over time, if the magnetic fields did not sort of act as a sieve, more than a sieve, really I would say an umbrella, trapping the charged particles from the solar wind in the outer magnetosphere. The solar wind particles would have come in and eroded the Earth's atmosphere away. So, the magnetosphere played a very important role in protecting the atmosphere, and is the geodynamo which enables this protection. So, with that, let me now come down to the sun, briefly recapitulate what we know. We know that the sun has these strongly magnetized regions which are known as sunspots, which have typical magnetic fields on the order of 1000 Gauss. We also know that outside the sunspots there is a somewhat weaker field which is on the order of tens of Gauss, and that this field permeates the whole sun and creates a sort of a dipolar structure which flips again every 11 years, just like the sunspot cycle, which tells you that this dipolar field flipping is also connected with somehow with the sunspot cycle. We know that the sunspot cycle has an average period of 11 years, but its amplitude fluctuates by quite a bit. We know that the magnetism of the sun governs much of the dynamics of the sun, which we discussed earlier, like solar flares, solar storms, solar wind, the coronal heating, its energy output. In fact, a lot of this is governed by sunspots, which is strongly magnetized regions. So, it is important therefore to understand where does this come from, where is this magnetic field produced, right. Okay. So, if you do not want to worry about the great details of this process, if you just want to have a very vague idea of how is magnetic energy generated in astrophysical systems through a dynamo process, you can simply sort of imagine this to a black box, the dynamo to a black box, which converts the kinetic energy of plasma to magnetic energy, which therefore produces magnetic fields. Now, is this something that is possible, such a mechanism? Yes, it is possible, because you have various sources of kinetic energy in diverse astrophysical systems, starting from the motion of ionized gases in supernova explosions, motions within the convection zone of stars, and motions within the ionized fluids of planetary cores, or even if it is not ionized, between the liquid highly conducting cores of planets, which can produce such dynamo action. Just to quickly review the magnetic field generation process, this is governed by the induction equation, which relates the magnetic field evolution to the velocity field and the diffusivity of the plasma. And as we have already discussed in the last module, when the magnetic Reynolds number in the system is high, the source term, which is the curl of V cross B term, dominates over the dissipative term, which is the eta lambda square B term, which implies that creation of magnetic field is possible, and whatever fields are created are sort of sustained against dissipation by the fluid flows, which is characterized by the velocity v in the induction equation. In fact, one can easily show that the magnetic Reynolds number is also the sort of the ratio of the diffusion time scale to the flow time scales. If the Reynolds number is high, the diffusion time scale is also very high, implying that diffusion is very slow in such systems. which again tells you that in such systems, if I create a magnetic field, it's first of all easier to create it, and then therefore, because diffusion time scale is very long, it is also easy to sustain these fields in this large scale astrophysical systems much more effectively. Also in the interior of stars or planets, the plasma beta parameter, which is the ratio of the gas pressure to the magnetic pressure, is very high, implying that the plasma flows dominate the dynamics and therefore can channelize its energy into magnetic fields. So, when these two conditions are satisfied, when magnetic Reynolds number is high, when the plasma beta parameter is also much higher than 1, the conditions that are necessary for magnetic dynamo action to take place are satisfied. And so, therefore, it is in this kind of a regime where solar dynamo action takes place in the interior of the sun, in the convection zone, where first of all you have these large scale velocities. So, you have a V, so you have a source term, and the magnetic Reynolds number is high there, and the plasma beta parameter is also high there, implying that the magnetic fields can be created by various sort of shearing, twisting, stretching motions, which follow from the induction equation, right. Okay, so, just to kind of give a brief history of the development of ideas in dynamo theory. So, the first important idea was the anti-dynamo theorem by Cowling, which sort of was a negative result, which showed that axisymmetric magnetic field cannot be generated or maintained by a steady axisymmetric plasma flow. So, this kind of a flow is very natural and is one of the simplest kind of flows, the axisymmetric plasma flows in spherically rotating systems, but Cowling showed that this kind of plasma flow cannot generate dynamo action. So, this sort of was a negative result which sort of played in the minds of people for many decades, until 1955, when Parker actually showed that if you have astrophysical systems where there is helical motions, then a process known as the mean field alpha effect, which derives its existence from the kinetic helicity of motions in rotating plasma systems, and which breaks certain symmetries in the fluid flow, sort of bypasses Cowling's anti-dynamo theorem and allows the generation of magnetic fields through what is known as the poloidal field creation mechanism, where the mean field alpha effect can create a poloidal component of the field from a large scale toroidal component, which sort of closes the loop of the dynamo, allowing sustained growth and creation of field. So, the way this occurs is alpha effect powers what is known as a mean electromotive force, which is the source which is responsible for the creation or destruction of magnetic fields, and the interplay of the mean field alpha effect with the turbulent diffusivity sort of provides the balance which tells you whether magnetic field creation is possible or not. And the alpha that you see here in the mean electromotive force in the first equation there, that alpha is, as you see, related to the helicity u dash curl of u dash, where u are the fluctuating velocity components, and the turbulent diffusivity eta is just a sort of a dot product of the fluctuating velocities, implying it is sort of related to the mean energy of the fluctuating velocity fields in the plasma domain. So, this sort of mean field treatment allows you to develop a concept of the dynamo as the mean field dynamo, which Eugene Parker and some other pioneers sort of laid down the basis of about 50 years back, which is still now widely used to interpret dynamo action in all of astrophysics. For example, the two coupled equations for the solar dynamo in under the assumption of axis symmetry. The first equation is the evolution equation for the vector potential for the poloidal component of the field. The second equation is the evolution equation for the toroidal component of the field. The various terms, I will not go into the details of that. You will get, you can get more details on these terms from the references, the resources that have been added at the end of this talk. It is suffice to say that these terms include both source terms as well as dissipative terms, as well as terms that describe the transport of magnetic fields from one part of domain to another part of the domain, stretching, twisting and shearing of the magnetic fields. So, the efficiency of the dynamo mechanism are measured in terms of dynamo parameters, which are sort of detailed here, where you can generate different kinds of dynamo number based on taking the ratios of different source terms to the dissipative terms, and based on what sort of dynamo is dominant, what kind of terms are dominant. You can classify the dynamo action into various kind of dynamos. For example, alpha square dynamos, alpha omega dynamos, and alpha square omega dynamos. In the Sun, where the differential rotation plays a reasonable role in contributing to dynamo action, we consider the dynamo to be alpha omega type dynamo, for example, and we can solve these equations in a computer with proper boundary conditions, and figure out how the magnetic field generation behaves. So, we know that the magnetic field is sort of created in the convection zone, which is out at 30% of the Sun, this layer, because the motions that you need, the V that you need in the induction equation exists there. So, the large scale motions are sort of present there, and in this region we are dealing with the full sort of plethora of possibilities of MHD, because you are dealing with magnetic fields as well as plasma flows. So, dynamics of magnetic fields in a plasma flow. So, essentially the kind of conditions that are necessary to drive dynamo action, MHD dynamo action, are all satisfied in the convection zone, and that is where all the action happens. So, without going into technical details, I want to tell you two important aspects of the dynamo action in the Sun. One is the creation of the toroidal component of the field, which is produced from the poloidal component, and this happens because of differential rotation. So, the rotation rate at the equatorial region, this region of the Sun, is much faster than the polar regions. So, for example, if you have a dipolar field, which you assume to be there initially, and it typically when a star forms from the collapse of a molecular cloud, you typically have a dipolar field which is brought in with the collapsing cloud, and if the system starts rotating differentially, then this magnetic fields, which are frozen in the plasma, because you are dealing with a high Reynolds number plasma, Alfvén's theorem flux freezing works, the parts which are frozen in the plasma will move faster. So, therefore, if the equator rotates faster, the field lines will get stretched in the equatorial direction, which means it will get stretched in the phi direction. So, the initially poloidal field will then create through differential rotation a toroidal component of the field, which is a phi component. So, this effect is known as the omega effect, where the toroidal component of the field is produced from the poloidal field by stretching due to differential rotation. Once you produce a toroidal component of the magnetic field, and you assume that I have a toroidal component, a toroidal flux tube in the interior of the star, because there is magnetic pressure associated with this flux tube in the interior. For pressure balance, the external gas pressure has to be equal to the internal pressure, internal gas pressure plus the magnetic pressure, right, which immediately implies that the density, which is like P is equal to rho r T. So, the density external to the flux tube must be larger than the density internal to the flux tube. So, the internal density is lower than the external density, right. Now, what this implies is that if I put a magnetic flux tube in a gravitational field, the flux tube would be buoyant, because its density is lower than the surroundings, and it will rise up. So, when it rises up, the magnetic flux tube will pierce the Sun's surface at 2 points, because it is continuous field lines. If it rises up, it has to pierce the magnetic surface at 2 points. So, at one point the magnetic field is going to come out, the other point is going to go down, right. So, you produce two sunspots. When a magnetic flux tube emerges, it always produces two sunspots of opposite polarity, one is positive, the other is negative, right. And during this emergence, this magnetic flux tubes are acted upon by the Coriolis force and the convective turbulence, which together produce this helical turbulence, which sort of powers the mean field alpha effect proposed by Parker, which literally catches hold of this toroidal magnetic flux tubes while they are rising up due to buoyancy, and twists them back into the poloidal plane, creating these small scale poloidal loops, which can then diffuse and recreate the large scale dipolar field or the poloidal component of the field, which is in the r theta plane, right. So, now I have first with differential rotation I produce the toroidal field out of a poloidal component, and through the mean field alpha effect I can recreate the poloidal field back, sort of closing this loop of dynamo action to allow the self sustaining process of recreation to proceed. It is also thought that another important process plays a role in the creation of this dipolar field. What we observe is when sunspots emerge on the sun's surface, they appear with a systematic tilt. For example, in the northern hemisphere, if there is a particular tilt, in the southern hemisphere the tilt is opposite, and the orientation of the sunspot pairs are also opposite in the southern hemisphere. Follow something which is known as the Joyce law and the Hale's polarity orientation law. Right here in this image, the positive regions are denoted by the white color, and the negative sunspots, the negative magnetic regions are denoted by the dark or the black colors. And you see that the systematic orientation of the bipolar sunspot pairs are opposite in the northern and the southern hemisphere, right. So, if you consider that and look at what happens when you have a systematic emergence of this tilted sunspot pairs in the northern and southern hemispheres, you realize that the spots which are the leading polarity spots in the direction of rotation towards the which are always closer to the equator would preferentially diffuse across the equator and cancel its polarity, whereas the following polarity spots which are at higher latitudes will preferentially diffuse and move with the plasma flows to the higher latitudes towards the poles, and therefore will cancel the old polar field and recreate the polar field of the new cycle, right. And this you actually see in action in observations, which is what is shown in the butterfly diagram of the observation of the evolution of the radial component of magnetic fields on the sun's surface. You see this sort of transport of opposite polarity flux across the equator, and then the leading the following polarity flux from high latitudes to the polar regions where they cancel out the old polar field and impart the new field, and this goes on repeating every 11 years very nicely. And this sort of links this dipolar field reversal, the large scale polar field reversal with the sunspot cycle, and this was something that was first proposed by Babcock and Layton and is now known as the Babcock-Layton process, which also plays a very important role in the dynamo mechanism. One last important step to be able to simulate the solar dynamo mechanism is to understand the flows in the interior of the star, and this is now possible through the field of heliosesmology, which allows you to probe the internal flows and the internal structure of the sun. These flows are constrained by these observations and then used in kinematic models of the solar dynamo, for example, where the velocities are prescribed to solve for the magnetic field, so that you can get an idea of how and where the magnetic fields of the sun are being produced. And when you do such a simulation, and this is a result of such a simulation that we have done in our group, here in color you see the evolution of the toroidal component of the magnetic field in the convection zone of the sun. This is the equatorial region, the north pole is up here, the south pole is down there, and in color what you see is the evolution of the toroidal field. The red is positive toroidal field, blue is negative toroidal field. You see this periodic reversal in the field strength and the creation of magnetic fields in the base of the convection zone of the sun and their transport towards the equator with what is known as the meridional flow, a large scale flow of plasma in the sun, which produces this equatorward propagation of sunspots and the butterfly diagram eventually. On this side, same domain, but what you see here is in solid curves positive or clockwise poloidal magnetic field, dashed curves are the negative or the anticlockwise poloidal fields. So, these poloidal fields are being produced when these toroidal fields rise up through the convection zone and reach the surface through the Babcock-Layton process and through a mean field alpha effect process which works throughout the convection zone. And this simulations is sort of seen to reproduce this sort of periodic behavior of the cycle, as well as the phase relationship between the poloidal field and the toroidal field. The poloidal field lags the toroidal field, and you see that clearly in this kind of simulations, which sort of tells you that you are getting the basic aspects of this dynamics right, although there are certain things we do not quite understand about the dynamo mechanism. We have made good progress over the last couple of decades. So, I will end there with some references to resources. The first one there, The Physics of Fluids and Plasmas, is a book that contains descriptions of both fluid and plasma plasma physics as well as MHD. The second one, this one is focusing more on the MHD dynamo. So, if you want to know much more details about the dynamo equations, their solutions and the recent state of the art in terms of knowledge, refer to this Living Reviews. It's a nice comprehensive article, provides further details on the solar dynamo mechanism.